This talk reveals the secrets of DDC, which is Digital Compact Cassette, and will show that the format is more than just a better sounding but less user-friendly competitor to microdisc, minidisc. Please welcome to the Hackaday Supercon stage, Jac Goudsmit and Ralf Porankiewicz. Probably butchered that, but.
Thank you, everyone. Like you said, my name is Jac Goudsmit. I originally came from Eindhoven, the Netherlands, which is also the hometown of Philips. I don't know if anyone knows what DCC is, the Digital Compact Cassette. Anyway, if you're here for the Dallas Cowboy cheerleaders, I'm sorry to disappoint you. I wrote the DCC FAQ page about a week before Philips discontinued the format. It hasn't had much maintenance. Last time I changed it was in November 03. I came to the United States in 2000. I've lived here since then. I also worked on the Wikipedia page, the English Wikipedia page for DCC. And this is my friend Ralf, and he's going to talk a little bit about himself and about the museum.
Yeah, you gotta love talking about yourself, right? So I run the DCC Museum, which is a volunteer-run museum about 90 minutes from here in Cathedral City. I came to the United States in 2009. I came for a job. Jac came for love. So pick whatever reason you find best. And in 2015, I found a couple of broken DCC players. There was no tutorials, no videos about them. And the only one who had done something was Techmoan. And it inspired me to start a channel, and that led to a museum. At that point, I discovered Jac while still thinking that he was in the Netherlands, and we turned out only to live like 45 minutes apart. So that was great. And then the collaboration started ever since. It's a museum 2.0, where we understand that not everybody can come to California to play with any of the players. Our museum is the largest one in the world that has all the working players and prototypes. Most of the cassettes are there, and we get like tons of visitors. Most of them are guys. They all come and play with equipment and talk about what can be done. What we do to keep the format alive is we still release music on what used to be called a dead format. So ever since 2017, we release 1 or 2 albums a year. In order to gain traction, we try to do that with, of course, artists that are famous or not famous. It really doesn't matter, but we pride ourselves in doing different type of packages. And there is sort of like a world championship of packaging. We won that twice. We competed twice. Last year, Billie Eilish was second and Coldplay was third. So if the jury really looks at packaging, it's sort of nice. And we won it with like a box. The interesting about the box is that it not only holds the cassette, but the artist did all the video work in a screen in the lid. Most interesting about this box is that this box is a collaboration with Sony, and Sony was minidisc and Philips was DCC, and they really hated one another. Which was unfortunate, because technically you could say that minidisc did win the competition, but in the end they weren't very successful either. Philips and Sony were in a loveless marriage that resulted in a beautiful child called a CD. That was a success, but when Philips rejected the DAT as a main source for a new format, Sony was so angry that they didn't want to join the DCC community, and they came out with minidisc. If they would have joined forces, who knows what could have happened. We rediscovered DCC, and the nice thing about DCC is that a lot of the key players are still around. They're all in their 80s. So what we try to do with our YouTube channel, we interview each and every one of them, have them tell their side of the story on what they think was success. Top left side is Peter Doetsen. He designed basically the CD case. So every time you open up a CD, you think of Peter Doetsen. I often think of Musetta Vander, who was the spokeswoman back in '92 for DCC. Abraham Hogendoorn was the inventor of the PASC audio compression, basically MP1. And a few of the team members, including Jac and me, of the volunteer in one of the meetings a couple of years ago. Before I hand it over to Jac, why is DCC so important, at least to us? I don't like when people try to rewrite history for the wrong reasons. When I found out that Matsushita Corporation, basically Technics and Panasonic, in their yearbook of 50 years of audio, completely abandoned DCC and Alcassette, that's when we decided to set the record straight, because Dutch people are not very well known for taking pride of their failures, and I think they should. I mean, you know, you go to Apple and you see a whole warehouse full of failures because that is what led them to their successes. Dutch people don't do that. I guess that's why we live in the United States now, right? Like, we upgraded. We passed the Dutchies on the left-hand side, so to speak. So you got that one. Okay, I practiced on it. It came up to me in the very last moment. So the DCC compression is basically MP1, and Philips tried to launch DCC, and as a plan B was the compression format MP1, which then led to MP2 and then led to MP3. And a lot of people think that Fraunhofer is mainly responsible for the MP3 format. That is not entirely true, and that's also why we are trying to preserve that part of the history and build onto that. So Jac is going to tell more about the real reason and the compression behind PASC, so I'm going to pass on the microphone to Jac again.
Yeah, this slide is just points out that the DCC Museum, basically Ralf made a documentary a couple of years ago, and we released it. This here is the theater on the Philips, the original Philips Not Lab, which is the science lab, the research facility of Philips, and that's where we had the premiere of the documentary. But if you scan the QR code, you can watch it on the internet now. Oh, latest news for the DCC Museum, we're releasing a cassette for the Dutch Swing College Band for their 75th anniversary. All right, the rest of this speech, I'm going to start with how DCC works, and I'm going to show you a little bit about the software projects. There's not much to see, so we'll mostly skip that. And then I have a project with a stationary recorder and a project with a portable recorder, which is quite unique because it was the only recorder that could be connected to the PC. So how does DCC work? So DCC recorder architecture, let's start with the head assembly. The signal goes from the heads. I'll tell you more about the heads and the way the design of the heads in a little bit. Those are connected to read amplifiers and write amplifiers. Those are all in one integrated circuit, and one is the read amplifier integrated circuit, one is the write amplifier integrated circuit. Those are connected to what's called the drive processor, the DRP. The DRP goes all the way from the analog signals and makes them into basically a stream of 384 kilobits per second in MPEG layer 1, which they used to call PASC. And that goes to MPEG decoder, and the SFC and ADAS work together as the MPEG encoder. If you only want to decode, you only need the SFC, and those are connected to a digital analog converter, digital digital input-output chip, and analog digital chip for recording from analog sources. All of this is brought together with a microcontroller that controls everything through an L3 bus, which is basically I2C. And there's also a DEC controller that controls the drawer motor, the reel motor, and a solenoid to switch functions of the DEC. And the capstan motor is controlled by the DRP, because while you play back something, the DRP has to make sure the bits come in at the exact right speed. Okay, the cassettes are basically the same size as analog cassettes. They don't have the little bulge, but they have a little slider, just like a floppy disk, if you remember those. And they got videotape in them. The recording heads are basically a circuit board at the chip level on a thin film substrate. So it's basically the current comes in here or goes out there, goes around, and then comes out there, and that's a coil for recording. And this here is the tape, moves like that, and the bits are stored as either full positive or full negative, so that makes it so that erasing is just a matter of overriding the tape, and you don't need a separate erase head to neutralize the tape first. Playback uses magneto-resistance heads, which is also used in hard disk technology right now. Philips worked together with Seagate, or at least they tried, and they went back to Seagate after a year, and Seagate said, we haven't done anything yet, and then Philips had to do it themselves. Watch the documentary. This is also basically on a thin film, so this is on a silicon wafer. The little square is the actual magneto-resistant element. There's a bias current that goes through each of the heads, and because of the magnetic flux from the tape, it varies the voltage, I think, of what goes of the current that goes through there. So it's a constant current, and the tape makes the voltage vary. Okay, so each head, because of the analog compatibility, they had 2 analog heads and then 9 DCC heads. These heads are for playback. The tracks are 195 micrometers apart. The playback heads are thinner, so that it's not a problem if the tape goes up and down a little, or the azimuth changes a little bit. Recording heads are wider, so that it erases and records the entire tape. So this is basically a diagram of what a head looks like. And when you look at a real head, it looks about like this in a stationary recorder. And they had a pivoting mechanism. And this whole head switches around to play the B side. All the DCC recorders are auto reverse. In a portable recorder, they put in a fixed head, and it has no less than 36 heads with nine tracks for recording, 9 tracks for playback, and that times 2 for each side. And then they used 2 of the DCC heads to play analog tapes. They couldn't get the analog heads on there, so they tried something different. Okay, here's some numbers about playing and recording DCC. Each data track has, there's 8 tracks with audio data. They start out being 96 kilobits per second each, a total of 768 kilobits per second. And there's a 9th track that has auxiliary information. And that's mostly used for envelope detection, so that if you fast forward the tape, it can read the signal from there and see that there's something there and stop on a marker. And the playback, during playback, there's the first thing it does is a synchronization, so it finds the beginning and end of each frame, and it does 10 to 8-bit demodulation, which means that it basically makes sure that the bits on the tape, there's the same amount of 0 bits as 1 bits, so there's no DC offset. Then when it gets that, there's a scattering of the bits across the tape, so in the various tracks. And there's also CIRC, what is it? I can't think of it. I'm sorry? That's it. Cross interleave read Solomon code. That's for the error correction. It's basically the same as for CD, although I think they use different polynomials. The resulting data rate is 384 kilobits per second, which is half of the original rate, plus 6 kilobits of what's called sysinfo. And the sysinfo can contain all kinds of interesting stuff like time codes, SCMS copy protection data, whether the pre-emphasis needs to be on, and also contains text, so song titles and stuff like that. On the auxiliary track, that runs at 1/8 times the original, the rate of the data tracks, so it results in 6 kilobits per second. And the auxiliary track can be recorded separately, so that's kind of nice. You can add markers later on without removing the music. Okay, in this presentation, I put everything that we discovered since 1996 or so in green. So we found out there was I was on a mailing list in the 90s, and we found out pretty quickly that the encoding of the audio was pretty much the same as MPEG-1 layer 1. But with the limitation that the bit rate was fixed at 384 kilobits per second, therefore you can't record in mono. You have to record in stereo, or in joint stereo, or in dual mono. And there's actually a feature in the DCC standard that makes it possible to record audiobooks or something where you have 4 what's called sectors per tape. So you go A, and then B, and then C, and then D, and you can put 180 minutes of text in mono, or music or something on a single tape. And the sample rates are limited to 32, 44.1, or 48 kilohertz. Need to drink some water, sorry. Okay, what's the difference? So at 44.1 kilohertz, the number of samples per MPEG frame is not exactly a multiple of the data rate. So there's padding that's needed. So in 44.1 MPEG-1, there's for every 49 MPEG frames, half of the 24 frames are longer than the others. And in PASC, we found out just recently that those extra frames need to be 0, and they can't contain data. For 32 or 48 kilohertz, that's not an issue. What DCC also has is DCC text, and every pre-recorded cassette has this, and they all have a little page on it that says DCC, the Digital Compact Cassette excellent performance is the result of advanced digital coding on a magnetic tape. DCC contains a completely new feature providing visual product information. And everyone's like, yeah, whatever, because there are no recorders that can record that can decode this. But every DCC tape, pre-recorded DCC tape, has this. And there's a couple of tapes that the DCC Museum has with some interesting text on it. For example, this one has Kermit the Frog singing in an animation. We have a DCC record. I'm sorry. This system is called ITTS, which is Interactive Text Transfer Service, and that was designed for digital radio broadcast, and it can do a lot of stuff. It was defined in the ISO 61866 standard, and that thing is $270 or so. It's like this thick. We have a decoder that can decode it at the museum, but no one else has one. So yeah, there's like 2 other ones in the world that got found. The one we have was from a mastering facility. It was used in a mastering facility, right? Yeah. So they basically, the standard said that every tape has to have it, and they had to check if it actually worked. So you hook up a TV through a SCART connector or something like that, and you could see what's on your tape. All right, my software projects. I had like 10 slides for this, but I reduced it to 1 because there wasn't really any information on the slides. I made 2 programs. One is to convert the PASC, so the DCC standard audio compression, to MPEG-1, layer 1, and vice versa. And I made another program where I modified another program called MP2Inc to encode wave to PASC. So it could already encode it to MP1 and modified it so that it could encode to PASC. I'll get back to that in a little while probably, if I can. All right, so I made some effort to reverse engineer a stationary DCC deck, and it might be interesting. Let's see, what's there to improve? Okay, so there's a couple of things that pre-recorded cassettes can do and user-recorded cassettes cannot. For example, on a pre-recorded DCC, the table of contents is written across the tape and on the entire tape, so that the recorder always knows where each track is and if it has to go to side B or not to find a track. Of course, that can only be done with a pre-recorded tape, because on a regular recorded tape, you record the songs one by one, and when you record the first song, you don't know where the second song is going to end up yet. The player knows which songs are on side B, and there's that DCC text information. On a user-recorded DCC, you can record track titles, but that feature was added to 3rd-generation recorders in 1994. The system came out in 1992, and that's incompatible with the earlier recorders. And you can only search by track number and not by song title, because the song titles are recorded at the start of each song. So as soon as the song is over, it forgets the other song titles. So what can't a user-recorded DCC cassette do? You can't see 3G recorder titles on earlier recorders, so that's a bummer. No recorders have an ITTS decoder, and only the 175, the portable recorder that I'm going to talk about next, has a facility to record titles on the fly. Text data from pre-recorded DCCs can't be archived. Even on the DCC 175, which is connected to a computer, you can't archive the ITTS data. And it's not possible for now to create pre-recorded tapes, but we're working on it. So this here is a 3rd-generation recorder. Came out in 1994. The nice thing about this is that it's got a deck inside it that's called a DDU2113, and that works pretty much all by itself to be a DCC recorder. Excuse me. The board here on top is the read and write amplifier. Then there's so that's the analog board, and the digital board is the board at the back. I'll get into that in a minute. And then the board in the middle is the deck controller. Okay, so the analog board, I don't have a good picture of that. It sends out a multiplexed analog signal of all the heads, and that's what you see in the top picture. And as it happens, we have a professional recorder that has the solid state version of a reed amplifier, and the board is like, I don't know, 12 inches by 5 inches or something like that. And so we know how that works. This is the deck controller. It just uses a Philips 8032 microcontroller. The 8032 is an Intel microcontroller, but Philips has a license to make as many of those as they want. And we happen to have a listing of the controller firmware. Okay, the deck controller is connected to the digital board with a serial port, basically, and it shows continuous data, basically, for tape counters, time estimates, and stuff like that. It can figure out what the tape position is within 5 seconds of starting to play a tape. That's kind of cool. The digital board is basically the heart of the deck. It's got the SPDIF I/O chip, so that's the digital audio input and output. It's got ADC, digital, so analog to digital, digital analog converter, PASC encoding and decoding. It's got a microcontroller, and it's got that drive processor that I was talking about. The drive processor, okay, I already said that it reads that multiplex analog signal from the read heads and does all this other stuff, and then generates PASC audio to an I2S bus, and sysinfo and aux-info to the L3 bus. When it's recording, it's basically doing all of that the other way around. The CPU is a NEC 78K, and it's connected to all the DCC chips, and it's connected to the front panel via sync serial, what they call sync serial, but it's basically SPI mode 3, so that's cool. And I made some connectors to break out that front panel connector, and put them on an ATSEM C21N explain board. Because it's 5-volt tolerant, and it has Arduino pins. I thought I might use that for a project later on for people to modify their own 730 deck. But unfortunately, I found out that it doesn't have any I2S bus, so unfortunately you can't tap the encoded audio with that. So I'm switching to something else. Okay, the bus between the front panel and the deck controller, the digital controller, works like SPI, but the devices don't transmit simultaneously. So yeah, whenever one of the two is not transmitting, you can just see FFs on the line, which makes it easier to see which way the data goes. Every message, I found out, starts with a byte that has the most significant bit toggled. So first command starts with, let's say, 80 and a hexadecimal, and the next command starts with 00, 0. Every message ends with a checksum, and that's just 1 byte. That's an XOR of the entire message, so it all makes it easy to do the reverse engineering. I found out that one of the first responses that the DDU2113 sends back to the front panel is the DEC identifier, and it's a byte FD, which means that means the DEC ID, followed by PHIL Philips 0001 NL for Netherlands 951 730. That's the 2 DECs that use this DDU2113. Star DDU2113 and U032. This is the that's the version of the software that's running on the DDU2113. Okay, so I was looking at all that data, and I thought it was kind of interesting that there were lots of messages coming by with 5F, 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 5F. That's decimal 95, and turns out that's a VU meter. So while you play a tape, it sends a VU values for the left and right channel to the front panel, even though the front panel doesn't have any VU meters. So that's interesting. Okay, the rest is just a matter of you know, decoding all the commands and stuff. The front panel basically constantly pulls the digital microcontroller for a status, and if something changes, it asks what changed. So, for example, there's a system status. For example, if it thinks that the heads need to be cleaned, the function changed. So, okay, I'm now playing. The drawer status, the drawer is now closed, the drawer is now open, etc., etc. All text to the front panel is in ASCII. So that's nice, because there are some that you can store the title of a track with the remote control, but there's a whole bunch of characters that you can't access through the remote control. So for example, the apostrophe, you can't enter that, so it's super stupid. But since the text is really an ASCII command, we could break in there and make our own front panel, and we can send apostrophes as much as we want. So yeah, basically I can do that. Okay, so I did this presentation before in 2019, and my original plan was, okay, what if we can just stop the digital processor on the DDU2113, and then take over the control over the DCC custom chips, but we pretty much abandoned that. The improved plan is to make another front panel. I found a panel that fits exactly. You can kind of see it. I'm holding it up in front of the deck, and it's the exact right size. We just need to, we have a problem that the Dolby decoder and the analog recording volume control are on the front panel PCB, so you can't just replace the whole thing. You have to replace the Dolby decoder. But this looks really cool. Picture doesn't do it justice. All right, the other project, this is basically, I've been writing about this on Hackaday.io. And so the DCC 175 was released in 1995 in the Netherlands. I got one on the first day that it came out. It's the only DCC recorder that could ever be connected to a computer, and it was only available in the Netherlands, so I was very lucky to have one. This is what it looks like on my 1999 Dell computer. This here is a 220 volt to 110 volt transformer. I don't need that anymore. This is the recorder. This computer runs Windows 98, and that's the only way it will work, because the program DCC Studio writes directly and controls directly the plug on the parallel port. So yeah, that's one of the problems, is it runs on Windows 95, 98, and no later versions of Windows. You need a parallel printer port. Emulation won't work. So if you put it in a virtual machine, nope, not going to happen. And those cables between the DCC recorder and the computer are extremely rare. We found out that there were 1,400 were made, and about 10,000 recorders. Yeah. Okay, so in the 90s, I started reverse engineering the DOS and Windows software that came with this DCC 175, and I didn't get very far. So a couple of years ago, I started with an approach from basically the other side, and start with the connector on the DCC 175 and go back from there. And it turns out that was pretty easy, because basically all it has is a serial port, which is also again SPI mode 3, and an I2S bus that has the PASC data. And we already know that the PASC data is basically MP1. So this was pretty easy, except there was a mistake in the schematic. These two buffers are for the subband digital audio data, and this one is SBDA out, and this is SBDA in. So this buffer was drawn the wrong way. It's supposed to go up. Okay, so after a bunch of trials to put this on my logic analyzer, I finally just hooked it up to a 9-pin DB connector, and I have it connected to a parallax processor, parallax propeller. And I made a program that basically just forwards all the traffic on the SPI bus to the PC. So yeah, I got I put everything on a turkey cutting board. So this is the turkey lab. I was gonna bring it along, but it's so much of a hassle to put it here somewhere and then let people look at it. So I didn't bring it. But it's got my 1999 computer. It's got the DCC 175. It's got a little breadboard with the propeller or whatever I want to put on it, and it's got the cable, and it's got the power supply for the laptop. So the SPI bus on the PC cable. I did some analysis with the logic analyzer and found out that there's starting with L3 ref. L3 ref is sent out every tape frame, and just after that it sends out 32 bytes with information. I was kind of thinking that this bus was kind of like a command response thing, where the computer said start playing or something, and then the recorder would respond or something. But no, that's not how it works. It just continuously sends blocks of 32 bytes of data. And I found out that thanks to a commenter on Hackaday called Vic, I don't know if you're here, but thank you. I found out that it basically sends the same blocks of information 4 times per tape frame. 3 of them I already know what's in there. Sorry, 2 of the blocks I already know what's in there. 1 of the blocks I still have to figure out. So what's the plan? I want to hook this up to a Teensy 4.x, a 4.0 or 4.1. I have both. This is 600 megahertz ARM processor, and it's got 3 SPI ports. It's got 2 I2S ports. It can do SPDIF, It can be USB slave, so it can connect to a computer, and it can be a USB host, so I can put it on a keyboard, so you can type song titles and stuff like that. And it's got a micro SD, so you can put a whole library of your grabbed DCC tapes on a SD card if you want. So how far have I gotten with this? Not very far, unfortunately. The good news is that I finally found some cables and the same connector that plugs into the back of the recorder, and they're still made, and they're not cheap, but they're still available, which is really cool. And I want to connect those to the Teensy, and connect the Teensy to a computer and maybe to a keyboard, and that will make it possible to grab some tape. All I need is some Windows software, and well, we'll see. Okay, that's about it. I still have many plans. There's so many ideas in my head. There's a lot of things that I didn't tell you guys. The main purpose of the project is to preserve tapes and to make it possible maybe to produce pre-recorded tapes. These are some addresses of where I'm at and where Ralf is at, and that's pretty much it. So,